Okay. Well, so do I, but I can't promise anything, though. Aharonov-Bohm effects in barotropic magnetohydrodynamics. Let's recall the Aharonov-Bohm effect, where we have an area in which magnetic field is null, curl of A is null, and therefore, naturally, A is a gradient of some function, but the function is non-single valued, and therefore, the discontinuity of this function is just a flux. Now, there is an example. Just take a round solenoid, as in 1959 Aharonov-Bohm paper, and you can calculate this S, and you can see that S is just proportional to the angle theta, which is a non-single value that's claimed, and everything is okay. Now, what are the main features of the Aharonov-Bohm effect? Well, you need a domain that is not simply connected, but can be made simply connected by introducing a cut. Mathematically speaking, the domain has a non-trivial fundamental homotopic group. Now, the electron or its wave function do not fill the magnetic field, so we have non-locality. The potential vector is very important. It's not just a mathematical tool, as emphasized by many previous speakers. It's a physical quantity, but it's a physical quantity which is a gradient of a non-single valued function. And gauge freedom is not gone, but it's only limited to single valued gauges. Another thing which I would like to mention before speaking about MHD is Bohm's causal interpretation of quantum mechanics. And there is a quantum classical correspondence in Bohm's interpretation, which is not a standard Copenhagen interpretation. There are not too many minutes, so I will not explain about this approach. But I would say only one thing, is that according to Bohm, the phase of a wave function should be interpreted as a potential of a velocity field. And I would like also to mention that one can take this correspondence the other way around and say that if a velocity field has a potential part, it can be interpreted as a phase of a wave function. I didn't say anything about MHD, but here are the equations of MHD. MHD is just Euler equations. Under a magnetic field, very good conductivity, so Faraday laws take the forms that you can see up there. Conservation law, you have 7 functions to solve for, nonlinear, very messy. I would like to give your attention to only one of those equations. Now, this equation, which is very known in mathematical physics, means that the field lines, in this case the magnetic field lines, are co-moving, and they move with the flow as it moves under the equation, and hence the topology of the field line is conserved. Okay, so if it has a complex topology to start with, you stay with the same topology. If it has a simple topology, again, it will stay with the same topology. Now, another thing I would like to draw your attention to is Sakharai's ideas. The idea of Sakurai is, let's look at the magnetic field lines and intersection of two surfaces, chi and eta. Myself and Lyndon Bell, in a paper from 2008, added another function which we call the magnetic metage. It's just a parameter going along this line. So you have a coordinate system which is connected to the magnetic field lines. Few minutes. Now,
I'm really sorry.
Okay. The magnetic field lines, well, let's say
It's not like a full presentation was it in the poster. So.
it will finish in just a few minutes, so it will be okay.
We have a bus in 16 minutes. And so
2 minutes and we're done. Okay?
I suggest that you go to conclusion.
Okay, I have to say a few things, sorry. Now?
No, look, we have to stop it because we have. I'm sorry. I'm sorry. It's a poster session, so it's 3 minutes presentation.
Okay, let's. The thing is, we have two topological constants in MHD, which are the magnetic helicity and the magnetic cross helicity. And if you solve for the vector potential, you will find out that there is a new function zeta, and this function essentially gives you the information about the topology. And, well, all this you can read in the poster session, and thank you for your time.
Thank you very much.